Hey, ladies and gents, let's continue on with looking at confidence intervals. It might be a good idea to go back and listen to the last video on, on the theory behind confidence intervals. Now we're going to get into actually working through some problems here. So this is on steps for constructing confidence intervals. And the part just above that is talking about how to calculate the Z alpha over 2 or T alpha over 2 values, which is from this formula here. So that's this part right in here. And that could be a Z value or that can be a T value. And again, that's based on your level of confidence. So if we have a 95% level of confidence, then you've got a 5% level of significance, and half of that is 2.5%. Remember, the level of confidence is we want to be 95% confident or sure that our interval, our confidence interval, contains the true mean. And then the 5% is the amount of allowable error. Why are we okay with some error? Because we can't be 100% certain unless we take a census. And that's a costly thing. It may even be impossible. You can't survey everybody in Canada. All right, so we have to be okay with being 95% certain of our results. Let's take a look down here about how to find those values on the Z or a T table. And so finding Z alpha over 2 then, so for a 95% level of confidence, then alpha would be 5%, and then alpha over 2 would be 2.5%. So the alpha over 2 is 2.5%. And so what you would do then is you subtract 2.5% from 0.5, and that would give you 0.475. You look up this value in the body of the table. A student from last year, or maybe it was the year before, said, hey, why don't you just simply take the level of confidence and divide it by 2, divide it in half. And that actually works really well. So 95%, 0.95, divide that by 2, and you get 47.5%. And that's what you look up in the body of the table. For finding the T value, T alpha over 2, remember these are just subscripts. So this is saying, let's say if it was a 95% level of confidence, then this would be 2.5%, 0.025. And then the n minus 1 is your degrees of freedom. And so it's not T times either of those two. Those are subscripts to tell you the column and the row that you're looking for. So this is the column, and this is the row on a T table. So what you do is you look up the alpha over 2 across the top to find the appropriate column. The degrees of freedom give you the row, and then the number there is your plus and minus values then that you have for the T. So let's work through a problem here. So the steps for constructing confidence intervals are slightly different for calculating probabilities in the earlier sections here. What you're going to find actually is that although there was a lot of theory to get us to this point about confidence intervals, the whole thing about the central limit theorem and the T distribution and the finite population correction factor, and then the theory behind confidence intervals, constructing confidence intervals is really easy, and it tends to be a part in the course on an exam where people get high marks. So they're really, really quite easily done. Let me show you how easy it is. Let's take a look at this class exercise number 11 here. Suppose the IQs of all college students are normally distributed with a standard deviation of 20. So this would be a sigma of 20. We're going to take a sample of n is equal to 25, and that gives us an x bar of 125. So notice the 25 and the 125 are sample statistics. They're in the sentence about the sample. We're going to construct a 95% confidence interval for the average, for mu. So let's take a look at that. Determine the characteristics of the population and the sample. So what we have is that, I guess I don't have to write down step number 1 since that's over on the side there. is x is normally distributed. That was here. We don't know what mu is. That's the whole point of a confidence interval, is to estimate mu. But in this particular case, we have a standard deviation. This is a sigma of 20. So that's what we've got about the population. And we are looking for, let's see, let's write down what we have about the sample. So n is equal to 25. We have an x bar equal to 125. And we're looking for a 95% confidence interval, CI, for mu. And that means that alpha will be equal to 0.05. That's your level of significance. Alpha over 2 will be 0.025. So that's what the problem gives us. Check the flow chart on the next page. This flow chart will be your friend. You're going to use this from this point on in the course. So this is what it looks like on page E22. In fact, let's go to the very end of the course here. So page 252, I think it is. And right there, okay. This is actually the formula sheet for your final exam, which is on units E, H, and R. And so you'll see actually the main part of it is the flowchart from page E22. That's almost all of it. There is some formulas at the bottom here. We've got an x bar and an s squared, which is back from unit C, because you need to know how to calculate a mean and a standard deviation. And then we've got some other stuff here from unit E. We will end that, end this particular unit with those. And then this stuff is from unit R. There's no formulas from unit H because they're actually all up here. That's what these are all about. Okay, so these are for hypothesis tests. This is for unit H, and then estimation is unit E, so confidence intervals. So that's what we're looking at here. I'm just going to erase these things before we get back there. All right. Let's take a look at that flow chart. I'll go back to the page where we first saw it, on page E22 here. And this is a flow chart that you're going to work through for all the problems from this point forward. And it will help you determine the formula that you're going to use. So, first question, is the population normal? If the answer to that is yes, then what theorem are we invoking? It's the first limit theorem. If the answer is no, then we ask this question, is n at least 30? And if the answer to that is yes, then the central limit theorem kicks in. Remember, it doesn't matter if what the original population looks like, as long as n is at least 30, then the central limit theorem applies. The first limit theorem applies if we know that the population is normally distributed, which would be told you in a problem, and therefore you can get away with any size of sample size, any sample size. If the answer is no, then this is SOL, statistically out of luck. You can't use a Z or a T. That doesn't necessarily mean that you can't solve the problem. It could be just a straight binomial problem. And so that goes back to a previous unit, right? But we're just going to be looking at Z and T. So all the problems that we're going to be looking at, the answer to that is going to be yes. We'll be able to get to this point here where we ask, is sigma known? If the answer to that is yes, then that means that we'll be using a Z distribution. If the answer is no, we said that's when you use a T distribution. And then the last question is capital N known? And that's the FPC factor, FPC. Remember, the square root of n minus n over n minus 1. So take a look at what we've got down here. So here's the part for confidence intervals right here. And so if Z is known, if sigma is known, then we're using a Z distribution, and that means that it's either formula 1 or 2, depending on whether we have an FPC factor. So we have X bar plus or minus a Z alpha over 2, and then your standard error of the mean, and that can include an FPC factor. If the answer up here is no, then we're using a T distribution. And then the question is whether we use an FPC factor or not. And that is formulas 3 and 4. So all we've done here is we've replaced the Z with a T, and of course the sigma with an S. So that's what we've got. So those are the ones that we're looking at this point. The next thing that we'll look at is actually we can do the same thing with proportions, binomial proportions, which is 5 and 6. So we'll get to that in the next little lesson. And then when we get to Unit H, these are the formulas that we'll use for hypothesis tests. And what I want you to note is that you've actually seen these before, right? This was what you were introduced to at the beginning of Unit H. This little knot here means that it is a hypothesized mu. And that's the only difference here. Okay, we've been introduced to the T distribution, the finite population correction factor. We will be introduced over here to proportions. So we'll get to that in Unit H. So not a whole lot else in terms of new formulas or anything there. Let's erase all that. And so that's what we've got up here. All right. Good. Let's let's take a look at our particular problem here, and it says it does say that it's normally distributed right here, and sigma is known here. It doesn't say anything about the size of the population. It doesn't say anything about big N. There'll always be a size here, but it'll be, in this case, a sample size, which is a little n of 25, but we don't have a big N, the population size. So let's go to the flowchart. And it says, is the population normal? Yes. Is sigma known? Yes. Is big N known? No. So the answer is that we're going to be using formula number 1 here. All right. So formula number 1 is down here, and this is just really the confidence interval that we were first introduced to. Let's go back and write that up. So this turns out to be formula number 1. And that says that the end points for the confidence interval, now you don't have to write that down, is just x bar plus or minus a z alpha over 2 value times sigma over the root of n. What I want you to notice about confidence intervals is they're always a point estimate and a margin of error. The margin of error is comprised of 2 parts. A z value, which is associated with your level of confidence, and then the standard error of the mean, right here. So that goes back to when we talked about that up here. So we saw that all up here. And that was in the last video. Now, we've got actually all of the parts that we need here except for the z value. So that's step number 3, is to find the z alpha over 2 value. So you wouldn't necessarily have to draw this out on a distribution, but this will help us in terms of learning this thing. So what we're saying here then is we're looking for a 95% level of confidence. So we're trying to find a Z value that has 2.5% in the tails. So in other words, if we have 2.5% here and 2.5% here, that leaves us with 95% in the middle. And of course, half of 95% is 47.5%, which a Z table gives us. So we would have 0.475 here. Now we also have it right here, but let's go to a Z table. And so here's a Z table. And actually, I just erased the answer there. So this is, again, if you have, 2.5% here, 0.025. You've got 47.5% here. Find the closest number to 47.5%. This one actually is right in there. And it's 1.96. So there's your Z value. Another place to find that is, we said, that if you go to a T table, the last line of a T table are common Z values. And there's the 1.96 at the bottom of the 2.5% column. So that would be 2.5% in the tail. So for common alphas, alpha over 2s, it's easier just to go to a T table. Go to the last line there. So 1.96. Let's go back down here where we were. And so the answer then is that this is plus and minus 1.96. Plug the values into the formula from step 2. So what we're going to have here then is x bar is, let's just go back where we had here. So x bar was 125, and then we had an n of 25, and we have a sigma of 20, and now we figured out the z value of 1.96. So we just go over here then and we say 125 plus or minus 1.96 times 20 over the square root of 25. Is that what it was? Yeah, 25. And that gives us, let me just grab my notes here, 125 plus or minus 7.84. So 125 plus or minus 7.84. This is your margin of error. And so 125 minus 7.84 is 117.16. And then 125 plus 7.84 is 132.84. So those are your lower and upper limits for your confidence intervals. The last thing that we're going to do is to write a summary statement. And I want to show you 3 ways to write it. So here's the first way. The first way is as a probability statement. And so it looks like this. It's important that if you write it as a probability statement that you get all of the parts in here. It's really easy to forget the P. It's really easy to forget the 0.95 at the end here. And a big mistake that people make here is putting the wrong symbol in here. So remember, you never have an X bar in there. You're never estimating an X bar. You're using the X bar to estimate the mu. So it's always a population parameter that you're estimating. And it's also not an X. I mean, when you take a look at earlier problems that we did, especially in Unit N, it was X, which represents the population, or X bar, which is the sample. But here we're estimating mu. So the second way of writing this is actually just how we would read this, and that is that we are 95% confident. So that's this part here, that the average, is this college IQs that we're looking at? Yep. That the average IQ of all, remember this is for the population, college students, is between 117.16 and 132.84. So that's how you write that then in words that people would understand. And that's actually just reading the probability statement, which is in blue. The third way of writing this is what I call the newspaper way. And this is how you would tend to see this reported in a newspaper. So the newspaper way says that, you can probably hear my dog barking in the background. The study shows that the average college IQ is 125. Okay, that's our point estimate. This is accurate with a 7.84 point, I guess if you're talking IQs, it would be points, right? Point margin of error. So that's this part right here, comma, there's one last part, 19 times in 20. And 19 times in 20 is 95% confidence, right? So that's this part right here. So you need to have all three of those if you're to write it that way. Now, let me show you where we've seen that kind of thing before. And I'm going to go back here to, what page would it be on? It'd be about page 12, maybe. How about the page before? Elvis lives in some example, in some minds. And this is what we have down here. Gallup says that the figures are accurate with a 4 percentage point margin of error, 19 times in 20. And it gave the original 10% up here. So that's the point estimate. There's your margin of error. And here's the 95%. When we take a look at how to do this in the next section, for proportions, we'll come back to this one and you'll see how that fits in exactly. Right now we're doing it for means, but this is how you would do it for proportions. So that's typically how they tend to write things in a newspaper article. And you should be looking for that whenever they talk about some sort of study. So that's what we've got there. And let's do one more problem here, and then I'm going to leave you homework. Number 12, a manufacturer of racing bicycles believes that the weights of the 500 bicycles, notice that it's not saying anything about a sample here. So this is a big N. The whole population, 500 bicycles, it produced this month are normally distributed with a standard deviation of 1.5 pounds. That's a sigma. Now we take a sample. So we take a sample, and so all of the numbers in this particular statement are going to be sample statistics. A sample of little n is equal to 30 bicycles gives us an average of 22.8 pounds. So that would be an X bar. What is a 96% level of confidence here for the mean, for mu, of all the 500 bicycles? So let's go through the steps. Step number 1. What do we know about the population? X is normally distributed. We are looking for the mean. The standard deviation is given to us, so that's our sigma, right, of 1.5 pounds. We have big N is equal to 500, little n is equal to 30, X bar is equal to 22.8. We're looking for a 96% confidence interval for the mean. That gives us an alpha of 4% and alpha over 2 of 2%. So that's everything that we know here on this. One thing to note here is that if you take a look at the fact that we have big N here, remember that if little n is at least 5% of big N, then you should be using an FPC factor. 5% means that if you multiply little n by 20, that would make it 600, and so our big N is actually less than that, so we should be using an FPC factor. As I've said to you before when we talked about FPC factors, if you're given big N, then just stick it in. It can never hurt, and it can certainly give you a more accurate estimate, unless it's absurdly high. If we say we're taking a sample of 30 out of 20 million adult Canadians, then that's your FPC factor will be so close to 1, it'll be 0.9999 something that it won't make any difference. Let's continue on. Step number 2. This is where you go to the formula sheet. And the formula sheet then is, we go to, oops, that's back, isn't it? Here we go. Is the population normal? And the answer is yes. Is sigma known? And the answer is yes. Is big N known? And the answer is yes. And so we're going to be using formula number 2 for that. I'm just going to erase those now so we can use this again. And so formula number 2 is this guy here. And that's the same as the one that we had above, except that we have this FPC factor tacked on there. So it's still a Z value with a sigma, but you've got this FPC factor there. So let's just erase that now. Okay. So this one is formula number 2, and you don't have to write down what number it is, but it would be a good idea to write this part down. That would be X bar plus or minus a Z alpha over 2 times sigma over the root of N times your FPC factor, like that. Now, again, this looks kind of ugly, but it's got 3 same parts here. A point estimate, this is the margin of error, and it's broken into 2 parts here, which is the Z value, which is associated with your level of confidence, and then this whole last part here is actually just the standard error, and it's adjusted because of we know the size of big N, and the sample size is a significant portion of big N. So it actually, this part here always turns out to be less than 1. So it makes the confidence interval smaller. So it makes your margin of error smaller. And so that means that we've got a smaller interval that we can be just as confident with than if we had a much larger population. So in other words, we know we've sampled a significant or a large portion of the population. And so that actually decreases our uncertainty, a smaller confidence interval. Step number 3 is where we would go over here and we would say, okay, we're talking about a 98% level of confidence. 96% level of confidence here. And that means that you've got 2% here and here. And of course, the Z table always gives you half of the 96, which would be 0.48. So that's a little easier, is just to take the 96% and divide it in half to get 48%. Let's go to a Z table. So here's the Z table here. And we're going to look for 48% here, because that gives you 2% in the tail, and then 48% from that point down to the middle. So that is 2.05. That's the Z value, which is closest to that. Okay, so this is plus or minus 2.05. Now again, you don't need to draw out this distribution in number 3 here. That's just to help you find the Z values. So on an exam, you can just simply write down that the Z value is equal to 2.05. Step number 4 is where we stick all these values into the formula. And so we say, okay, let's go back to blue here. We've got our X bar given to us, which was 22.8 plus or minus 2.05 is that Z value, times sigma 1.5 over the square root of 30, that's little n, times your FPC factor, big N, 500, minus little n, 30, over 500 minus 1. Okay? I'm going to delete this here. And that gives us 22.8 plus or minus, and this whole thing on the right-hand side. Pull out your calculator, and you get, what do you get? 0.54. That's your margin of error. And so 22.8 minus that is 22.26. Plus that is 23.34. I usually take it to 2 decimal places. Because the original estimate was to 1 decimal place, you could actually just take it to 1 decimal place, because that's the number of significant digits. I'll leave them as 2 decimal places, which is just a standard that we can use here. Let's write summary statements. So on an exam or an assignment, you'd only have to write one of these, unless you were told to put it in words that a non-statistician understands, in which case you wouldn't use the first one, which is a probability statement, but you could use either of the other two. So here's a probability statement. Remember, the thing in the middle is a mu, not an X bar or an X. And don't just leave it there, because what that says is the probability that mu is between 22 and 0.26 and 23.34 is what? Is 95%. So that's, you want to finish the statement off like that. Another way of writing this then is So that's one way of writing the answer. Here's a second way, and that is just reading this out. We are 95% confident or certain that the average, what are we looking at here? Weights of the 500 bicycles, that's your population, is between 22.26 and 23.34 pounds. And let's see if we can squeeze in here the newspaper way of writing this. So the newspaper way would be, the study shows that the average weight of the 500 bicycles, bicycles, that's how you spell it, is 22.8 pounds. So that was your X bar value. This is accurate. With a 0.54 pound margin of error (96%). So what you do is you reduce that as a fraction. 96% would be, let's see, 96 out of 100. Let's half that. So that'd be 48 out of 50. You could half that again. I guess it's 24 times in 25. Now, so that's 96%. 24 out of 25 is 96%. That's your level of confidence. And again, here's your point estimate, right? That was your X bar. And then here's your margin of error. So you got your three parts there that are necessary if you write it that way. By the way, a 96% level of confidence is not common. And so if it was 90%, you would say 9 times out of 10. If it's 95%, which is most common, you say 19 times in 20. And if it's 99%, you would say 99 times in 100 or out of 100. So that's what we've got. That is the end of that problem. That leaves you with one more here. So I'd like you to do number 13 for homework. And that will then take us to estimating the population proportion. So doing the same thing with proportions. So let's end it there.